In this lecture, we will examine the proof of the Cantor-Schroeder-Bernstein Theorem. In the theorem, we are given two sets A and B, a one-to-one function f from set A into set B, and a second one-to-one function g from set B into A. Nothing is mentioned about whether or not f and g are onto. The Cantor-Schroeder-Bernstein theorem states that there exists a bijection H from set A onto B. In other words, H is one-to-one from set A onto set B. We start the proof with an element a sub 0 from set A. Since the domain of the function f is set A and the range is a subset of set B, there should exist an element b sub 0 in set B such that f of a sub 0 is equal to b sub 0. And since the domain of the function g is set B and its range is a subset of set A, there should exist an element a sub 1 from set A such that g of b sub 0 is equal to a sub 1. By the alternate application of the functions f and g between sets A and B respectively, we generate a sequence of elements from set A alternating with elements from set B. Of course, we could have started the string with an element from set B instead and generate a similar sequence of elements. So the alternate application of the functions f and g on sets A and B generate what we call directed graphs. There are 6 different types of directed graphs to consider. The 6 different types of directed graphs pertain to the shape of the directed graphs that we obtain by the alternate application of the functions f and g on sets A and B. We will break down the proof according to which graphs are feasible under the conditions given to us in the theorem. The first type is a directed graph that has a starting point, such as the ones shown on the left. If the string were to start with a sub 0 from set A, the assumption is that there is no element b sub 1 from set B such that g of b sub minus 1 equals a sub 0. The same thing can be said if the string were to start with an element b sub 0 from set B. For this type of a string, there is no element a sub minus 1 from set A such that f of a sub minus 1 equals b sub 0. The second type of a string is a string with no starting point. When we talk about this type of a string, we exclude the possibility that the directed graph forms a loop within itself. Observe that every element A of set A has a corresponding element B of set B such that g of B is equal to A. It is also true that every element B of set B within the string has a corresponding element A of set A such that f of A is equal to B. It is conceivable with the nature of the functions f and g that these linear strings can go on indefinitely, unless the graph forms a loop. This is now the third type of directed graph. It is possible that a loop intersects a linear string, or a linear string can loop on itself, forming a directed graph such as the one shown on the left. This is the fourth case, and we will treat it as a loop intersecting a linear string. The loop and the linear string can intersect at a single element from set B, or a single element from set A, or at multiple elements from both sets. It is also possible that the two types of graphs intersect transversely. Before we present the fifth and sixth cases of directed graphs, we will first prove that case 4, where a loop intersects a linear string, is impossible. Without loss of generality, let us assume that the loop and the linear string intersect at the element b sub 0 from set B. We also assume that the loop and the linear string separate at b sub 0. On the linear string, g of b sub 0 is equal to a sub 1. On the loop, g of b sub 0 is equal to a sub 1 prime. If indeed the loop and the linear string separate at b sub 0, then a sub 1 cannot be the same as a sub 1 prime. This would be a contradiction because g is a function and can assign only at most one value to b sub 0. And so case 4, where a loop intersects a linear string, is impossible. The fifth type of directed graph is when we have a linear string intersecting another linear string. Assuming that the linear strings are not identical, then we take a look at a few possibilities. We can have the two strings intersect first, and then eventually separate. One should be able to see the similarity between the graph shown on the left and that of case 4. And so we should be able to show that the graphs shown on the left are impossible by using the same idea that we used to show that case 4 is impossible. There is one other possibility in that the two linear graphs stay distinct at first and then eventually merge. Let us suppose that the two strings merge at an element a sub 0 of set A. Along one graph, g of b sub minus 1 is a sub 0. Along the other graph, a sub 0 is also equal to g of b sub minus 1 prime. The assumption here is a sub 0 is the point at which the two graphs start to merge, so that b sub minus 1 cannot be equal to b sub minus 1 prime. This is a contradiction because the function g is 1-to-1. G cannot assign the same element of set A to two distinct elements of set B. We would also get a contradiction if instead of a sub 0, the two graphs merged at b sub 0, an element of set B. And so it is impossible for two distinct linear strings to intersect. For the final case, we have a loop intersecting another loop. There are other configurations for two distinct loops to intersect, different from the one that is shown on the left. But regardless of how the loops intersect, we can show that two distinct loops cannot intersect by using the same ideas that we used to show that cases 4 and 5 are impossible. And so we just have to work with the first three cases. We have linear strings with starting points, linear strings without starting points, and loops. All these graphs are mutually disjoint. This also means that two graphs cannot intersect unless they are one and the same graph. Furthermore, all the elements of A and B belong to the union of all of these graphs. We should be able to define an equivalence relation on the union of A and B with the individual graphs as the equivalence classes. We now define the bijection H from set A onto set B. The bijection H will be a piecewise function defined differently for each type of graph. Consider first the linear string that starts with the element a sub 0 from set A. For every element A of set A that belongs to this string, we define h of A to be equal to f of A. H is 1-to-1 within this particular type of string because f is 1-to-1 over the entire set A. Now suppose that this time the string starts with an element b sub 0 from set B. Observe that b sub 0 does not have a pre-image under f within this string. Therefore, we cannot use h equals f within this string, because as such h would not be onto. We have to be a little bit more creative in defining h within this string. This time, we use the function g in defining h within this string. The domain of g is set B. So for every element b of set B within this string, there exists an element a of set A, such that g of b is equal to a. G is 1 to 1. Therefore, G inverse exists. And so G inverse of A is equal to B, and we define H to be equal to G inverse on this string. H is 1 to 1 on this string because G inverse is 1 to 1. It is a simple exercise to show that G would not be a function if G inverse were not to be 1 to 1. Before we define H on the other types of strings, let us first take a look at the possibility that H will not be well defined, because H is defined differently on different types of strings. What is key here is the fact that these directed graphs are mutually disjoint. Each element of set A belongs to exactly one directed graph. Each directed graph, and therefore each element of set A, will have a unique definition of H assigned to it. The case of a linear string with no endpoints is a lot more straightforward. Every element of set B within this string has a pre-image within set A. And so for every element A of set A within this string, we define H of A to be equal to F of A. Now H has to be 1 to 1, since F is 1 to 1. The case for loops is just like that of linear strings with no starting point. Every element of set B within each loop has a pre-image within set A. And so we define H of A to be equal to F of A. Since F is 1 to 1, H is also 1 to 1. And there you have it. We have defined H as a piecewise function which is made up of 4 different parts. The function H from set A into set B is guaranteed to be 1 to 1 because H is 1 to 1 on each individual piece. And the individual pieces are mutually disjoint. The only thing that we need to show is to show that the function H from set A into set B is onto. Each element of set B belongs to a unique specific graph, and so we will show that H is onto for each specific graph. The first graph is a linear string that starts with an element of set A. On this type of graph, every element of B has a pre-image. B, which is equal to h of a, is equal to f of a. The second linear string starts with an element of set B. This time we go in the opposite direction, and h of a is equal to g inverse of a. For the linear string with no starting point, h of a is equal to f of a. And finally, we have the loop. H of a is also equal to f of a. Now that we have shown that every element of set B has a pre-image in set A under the function h, h is therefore onto. Because the function h from set A into set B is both one-to-one and onto, h is a bijection.